Hi, so welcome everybody. I'm really pleased to be kicking off on this sort of workshop on simplifying system-on-chip design and manufacture between ourselves and CMC. The three presenters, I'm going to start off and give a background in terms of SoC Labs, how we perceive that simplifying SoC design by reusing both IP and design IP, but also in terms of the development environment and how we maintain the development environment in which to design our SoC systems. Daniel's going to sort of take over and then take us through some detailed activity around the nanoSoC reference design. And then Oleg is going to follow up in terms of how CMC can support the design environment and also provide pathways to manufacture. So let's just sort of start with the integration challenge. So anyone that's sort of taken part in designing an SoC and getting that all the way through to tested silicon and back knows that it's quite a challenge to set up and maintain the environment within which you design, as well as undertaking the design and doing all of the verification. And it's a challenge that certainly in academia we can often be not well prepared for. So if you're just starting out on that, if there were people that are sort of PhD students on the call, it's quite a challenge to get all of the things in place that you need to get in place just to get the design started. And this is sort of well known and understood, I think, by many people in the industry in terms of the tool providers, so the EDA tool providers, the IP providers such as ARM, who we're supporting today, and the foundries in terms of how we access them. We also struggle a bit in academia in terms of retaining that knowledge from project to project. And if you look at how things happen in industry, projects usually build on each other. And they reuse a lot of design and a lot of their project environment. And what we want to try and do is encourage how we can share that across academia and also help startups to be able to take part. And that's what we're going to try and discuss today. It's a challenge that's well recognised by the industry. So again, part of what we're here to do, working today with CMC, is under a thing called the Semiconductor Education Alliance, and that covers significant players in industry such as all of the major EDA vendors, ARM in terms of compute IP, CMC. In terms of pathway to manufacture and support in terms of EDA tooling. So we're really pleased to try and help resolve that challenge, and we're working on that and working again with academia and startups to improve that. So let's look at how we sort of minimize that adoption challenge that I mentioned. Again, one way we can do that is to look at what we call reusable reference designs. So ARM, through the ARM Academic Access Program, has provided access to IP for academia and startups that covers quite a broad range of their compute subsystems, everything from the simplest microcontroller up to a quite complex A-class Linux processor. And that's a full IP that we can get and utilize. But just having that IP doesn't allow us to simply then make a SoC. There's a lot of other activities we need to understand to make a SoC. And even though that IP comes pre-verified, there's still a lot of verification work that certainly within academia we can struggle to actually have knowledge of and have assets to deploy to verify those designs before we take them out. So what we're doing within SoC Labs is building those verification assets, building up some reference designs, but also trying to work with all of the partners in terms of pathways to manufacture or EDA tool providers to really simplify the problems such that we can make it really easy to adopt. And part of that is a view about how you might virtualize a development environment such that you can utilize it again and again over projects. ARM provide all that IP for free. There's no license charge. There's still a licensing action you need to go through, but that is done by each university institution. It doesn't have to be done each time you start a project. So it's just started up at each institution. And again, we can help you with that if there are any issues. So just to give a bit of background about SoC Labs, if you look at this structure at the top of the slide, that's actually the structure of our website. So if you go to SoCLabs.org, you'll see that actually we've structured the presentation just like we structure the website. So everything you hear today, you can go and refer to our website and understand. So first thing is what are we about? So we're a global academic community for a system-on-chip design using the ARM ecosystem. And as I've said, what we want to do is make it really simple to take your SoC design, whatever that might be, custom accelerator for AI, ML, or a sensor, and make it easy to transition from a concept all the way through to tape out. And again, to promote how we can get best practice across academia in terms of being able to do these types of activities. We've got some uniquenesses. So I know there are some industrial partners on the call. But just like if you were trying to deal with requirements for any particular market, there's some particular markets about the academic community that are quite different in terms of our need to get academic output out in terms of proven silicon results in tier 1 publications. And some of what we do guides to that. But fundamentally, this whole thing is backed up by the semiconductor industry to help us all out. So as I said, this is what we're trying to do, help solve these integration challenges in terms of both reuse of design IP, but also our project development environment. So where have we got to? So we're about 130 institutions globally so far. We're across 34 countries, and we currently have 25 projects. Our reference designs have been fabricated at nodes such as 65 nanometer TSMC, and we currently have 2 in physical tape out. We have others planned, and Daniel's going to go into that in a bit more detail. So what we tried to do in terms of actual SoC designs was to look at the ARM portfolio and come up with a simple way that we could provide reusable reference designs that is very easy for the academic community to adopt. I often use an analogy that it's like going into a car rental. There's a whole bunch of cars, but usually they just say, do you want a small car, a medium car, or a big car? And so that's what we've tried to do. And so nanoSoC, which we'll talk more about in a moment, is actually an entry level. It's a microcontroller type reference design. It's very easily adoptable by a simple, application, can be undertaken by a PhD student or a master's student in about a year. Very low budget, but obviously, it has limitations in terms of what it can do as a compute platform. At the other end of the spectrum, there are people that are interested in, complex AI, ML, video applications, and they need a much more competent platform. So that what have we produced nanoSoC for? But you're going to need more resources and more capital to actually get that underway. And so you're more likely looking at a sort of research group that they're undertaking that. And nanoSoC is in the middle. Daniel will give a bit more detail about that, but it's mainly around sort of real-time DSP type applications. So that's sort of roughly a view of SoC Labs. I'm going to hand over to Daniel, and he is going to sort of take you a bit more through the actual details of nanoSoC and how you get a SoC fabricated.
Hi everyone, hopefully you can all hear me. Thanks John for the intro. So I'm going to start by taking a bit of a deeper dive into the nanoSoC and what it is. Like John said, so this is all from the ARM Academic Access Program. One of the things that they provide with that is their cornerstone IPs, and these IPs are subsystems. The most basic one being around the Cortex M0, which they call their CMSDK or their Cornerstone 101. What we've done with that is we've taken their design as, you know, sort of inspiration, a starting point, and expanded it into a full SoC and a full system. So yeah, so this is based around the M0 processor. What we've added in support for some DMA. So there's a couple of options of DMA controllers, and to allow you know, low power data movement through the system without relying on the CPU to do that. We've expanded a bit in terms of the peripheral regions. So this is then like your UART timers, all things you need really for software. And on top of that, we've added in a few things for sort of academic needs. So one of these being the SoC debug controller. That's an IP that we've designed, which helps sort of validation of the SoC without having to need any sort of boot up of the processor or the DMA. You can just directly go in through the debug controller to access anywhere in the address region over the bus. And then adding in this sort of expansion region where, you know, we've sort of said your accelerator goes here, or you know, your subsystem goes here, with its own sort of dedicated SRAMs. What we've done, you know, sort of achieved so far with nanoSoC. So we've had 2 tape outs of this 65 nanometer. One of these was completed by a PhD student. This is in his first year of his PhD. His accelerator was based around K&N classification, so he's doing a hardware implementation of that. And in terms of, you know, what the sort of metrics he got out of that is that his, you know, custom accelerator sped up from 10,000 milliseconds to 3 milliseconds of compute time. And a master's student as well. So what their project is called the Hellfire Stochastic Array. So this was a small systolic array system for ML or AI ML using the DMA mainly for transferring quickly data through. And so both of these using the same nanoSoC reference design. Some slight differences and slight customizations. I think that's one thing sort of important to note is that nanoSoC, the way that it's provided by us is full RTL from ARM through the AAA program. You get access to full RTL, so you can make any changes that you want throughout the system if you see fit. Other projects, these are currently ones that are ongoing. So there's quite a few spaces or applications that nanoSoC can be used for. So obviously there's a big boom in AI and ML accelerators. So we see quite a lot of people doing things around this. And particularly, I think for academia to get funding, you sort of need to put AI in your funding proposals at the moment. But as well as that, you know, we get to have some mixed signal projects. So particularly for sort of agriculture, and quite an interesting project on the use of machine learning with the distributed nodes for compute in grocery transportation. On the website, you can see all the projects. Everything is sort of open to the public, and you can read through how they're going. We try to encourage them to keep everything up to date so that you can sort of see how things are going. On a bit of a deeper dive, so this is a project with ARU, so it's Anglia Ruskin University. Their accelerator was generated using the HLS4ML framework. And what we've been doing with them is, you know, providing as much support as we can and going through this process of generating code, taking it through to backend and doing this sort of iterative process to try and really refine what the sort of generated code is doing. And I think I just wanted to highlight here a bit in terms of what you can do in the back end is really sort of investigate how your floor plan affects your performance, how you can look at kind of things like how the clock gets distributed. That's in the, sorry, I should probably do a pointer here. So this is the sort of version 1 floor planning, and this is the clock distribution tree. So you can see sort of the green is the top level, the blue second level, and then third level is in red, which is, you know, obviously nice for debugging. It's also quite nice for just having good pictures for publications and for sort of presentations like this. To talk a little bit more about the SoC debug controller that we've made for this. So like I said, so CMSDK, or the Course Name 101, provides the basic subsystem. And what we've added here is then a debugger that you can use with, the CPU not booted, basically nothing else working. This gives you full access to all of the subsystems to see, you know, for debug if it's not working, or even just like a simple way in to transfer data in and out of the system. And the way that we've, you know, implemented this is to support a sort of simple USB UART adapter, whether that's from your PC or Raspberry Pi, things like that, as the host driver. And then a kind of robust, what we've called this XIO 8-bit bus interface. This is effectively a, you know, axis stream interface, but it allows for good sort of robust data movement across the pins. So again, kind of in the theme of reusability, with the post-silicon testing, what we've done is created a test board that uses a standard pinout for nanoSoC. So in this, you know, the socket in the middle here, you can take out this and put in another nanoSoC chip, and it will work, you know, just as expected. This design for the board effectively mimics what we're doing in the test bench for the behavioral design. So in terms of verification assets that they created at the start of the project, you can use those all the way through. You can measure power from the, you know, your accelerator as well as the rest of the SoC, as well as, you know, sort of standard communication in over USB here. And just to touch a little bit more on our other reference designs, so like John said, so MillerSoC is our kind of middle reference design. This was really driven, the sort of design of this was really driven by the need for higher data bandwidth in the system. So these are kind of looking at applications, so yeah, real-time audio or like RF. We had some interest in RF, like beamforming, some bigger AI or ML models or processing where you need, yeah, a lot of data movement or other kind of digital signal processing. Like I say, so the need for the higher data bandwidth we've gone with this is then to use the full AXI system. So this has then got the NIC 400 as the bus interface, the bus subsystem. And for the CPU, we've tried to make this so that it's kind of swappable from the M7, the M55, and the R5, depending on the sort of need of the application or the need of the project. And this, in terms of software, I think so nanoSoC, it's really just sort of bare metal programming. This sort of size SoC, the idea is so that this can use some sort of real-time operating system, a very sort of lightweight operating system. And going on to MegaSoC, so the application for this is really more where you've got, you know, very complex software stack, or you're trying to move, you know, really significant amounts of data, so things like real-time video or larger AI models. The driver for this was to have a sort of full Linux capable system. So in terms of the design choices that we've made, that's really what's been driving it. And we ended up on the Cortex A53. I think a lot of people are quite familiar with this processor, as it's used in a lot of like the Zinc FPGA platforms, and it's got good, you know, performance and sort of efficiency for that kind of class of processor. And I think the other thing to say is, yeah, the high memory bandwidth, but then high memory capacity. So that's why we've got the DRAM in this, which adds complexity, but I think it's needed for this kind of class of design. So that's kind of talking through, the technology, so we call it. So we break this down, as projects, technology, design flows. So the reference designs and all of like the IP, that's one of the technology sides, and then we sort of apply those to the design flows. And this is how the website is structured. This is how a lot of the stuff we talk about is structured. On the website, you'll see that these are all broken down into sort of generic stages in terms of how to achieve each of these. These all have their own sort of subtrees of what's in architectural design, what's in behavioral design, logical design, etc. Inside of all of those steps, we've got examples for tool-specific flows or steps, commands, or anything like that, as well as specific, sort of how this is done in nanoSoC versus how this is done in other sort of systems. The website in general, anyone can make any edits to any of the pages. Obviously, it's all moderated, but you can go in and add any sort of information you want, and we do encourage people to do that, particularly more senior engineers or just anyone who's got experience with those kind of flows or technologies or anything like that. And a thing that we noticed as well in academia, which industry tends to do quite well, academia not always so much, is project organization and project management. So really here, the sort of project structure side is built around the efficient reuse of IP, scripts, sort of environment setup, and to enable this sort of collaborative working, so you can separate things out properly and have people working independently on different tasks. So this, for instance, this project structure here is for sort of nanoSoC. The way that we've done this is we've got repositories for the FPGA libraries, the ASIC libraries, nanoSoC itself, and then some other sort of wrappers and RTL primitives. Those are the sort of technology repositories, and we have some flow repositories. We've got actually a couple more here that aren't listed. And then in the sort of top level of this project, you have scripts that just set up the environment for that specific project. So then it makes certain tweaks to the files in these other repositories, or changes variables so that it gets set up specifically for this project. In terms of the project management then, on the website, so if you create a project there's a section for milestones, and on the project pages you'll see this kind of traffic light system which could show which bits are completed, which are in progress. Sometimes things aren't needed, for instance, the IP selection side, if you already know what you're doing, that's completed, or if you're, if it's just the thing on creating a certain piece of IP, if that's your project, then that's not quite as necessary. The real highlight from this is, and why we wanted to do it, is in industry, what you might do is if you're starting something, so let's just say you're starting synthesis, you might talk to one of the senior engineers at your company to see how long is it going to take, or what things should I look out for. What you can do on the SoC Labs site is you can see what other projects, how long they took, what kind of results they've got, and sort of apply that to your own project to make estimates, or see whether things are feasible or not. We encourage people as well to talk about what their areas are like, from the P&R and everything, so that you can sort of get estimates of budgets you'll need for projects. like so this is sort of going on more from what I was saying. These are a couple of examples from the website of projects. So this is one from the University of Sydney. Who've been really good at keeping up to date on all their milestones and giving sort of good information to other people in terms of how they've done things, where they've tripped up on things, and hopefully that's helping other people learn from their sort of journey through it. And as well as IATH have got a larger scale project, so they're doing a A53 at TSMC 28 nanometer node. They've been very good at sharing how they've configured things, and what that means in terms of the area usage, timing closure, things like that, which again you can freely look at and apply that to your own projects as well. The Git, all of what we do is in the open domain, like I've said. So our Git is free to look at all of the projects there. The way that it's structured is in terms of projects, technologies, and flows, very similar to the website. So in terms of projects, you'll see sort of top level reference designs for nanoSoC, milliSoC, and megaSoC. You'll also see forks of those projects. Say, for instance, in the nanoSoC project, there's a fork of that with a accelerator implementation of AES encryption engine. And I think there's a few more there as well. That's effectively the top level that if you're wanting to use the full reference design, that you should copy or fork those. Technologies, these are then subsystems or systems that are used in the projects. So we have nanoSoC tech repository, or we've got the DMA 350 tech repository, which has some configuration files and wrappers for the IPs, and then flows. So these have scripts and etc. to perform flow steps. Some of them are just really simple, Python scripts that build up file lists using the tools, which we just rather than rewrite those for each of the projects, we've got them reusable across anything. And obviously, we've got the reference designs, but also if there's things in there that are useful to you that you want to take across for your own projects or your own SoCs, feel free to do that. So now actually sort of using nanoSoC, you can treat it like a black box in your sort of architectural, in your design of your own IP. The interface to the expansion region is, so there's an AHB interface, there's some interrupts back to the CPU, and some DMA request pins. You can kind of obscure the view of nanoSoC and just think that's basically your test bench for your IP. If you find that it's not quite what you want, if you want to change the SRAM sizes, you want to change the sort of configuration of the DMAs or anything like that, again, like I say, it's all open source. You can go in and make any changes that you want. And then in terms of the verification flow in nanoSoC, we found people do it in one of two ways. So you can either develop your IP inside the nanoSoC framework. So then, like I say, you're kind of using nanoSoC as the test bench in effect. So you're driving test vectors from the M0 CPU into your accelerator and reading it off that way. Alternatively, you can develop this in your own environment. If the top level ports stay the same, it doesn't make much difference. We found it's slightly quicker if you do the development and verification within nanoSoC, because then everything's already integrated by the time you're sort of finished with it. But again, I think it's a sort of choice of preference there. Data flow is something that we usually ask quite early on what the kind of data's like that you need for your accelerator. What's the volume? How quickly does it need to be driven? How best is it to drive? So in nanoSoC, effectively, there's three ways that you can drive data. You can either use a CPU, which is simple but a bit higher power solution. You can do DMA driven data movement, generally lower power, obviously slightly more complicated in the software. And then you can use the SoC debug just to directly drive your expansion region. In terms of behavioral verification, the nanoSoC comes pre-verified, at least in the configurations that we've done. Obviously, if you make changes to it, that's it's sort of at your own risk. The only thing that needs verifying effectively is the IP that you put into it. The test bench for nanoSoC goes all the way up to the pad level. So really, when you're sort of looking at this, it's effectively like you've got a test bench with your silicon chip there already. And the reason that we've done this is that every sort of stage through this, we try and keep it as the full chip, including the pads. So behavior verification, FPGA, up to then post-silicon verification. So any of the assets that are created as you go through those steps, whether that's firmware or sort of these RX, TX comms, things like that in the test bench, they can either be directly used throughout the whole stack or replicated in slightly different forms. At least you've got a good starting point then. We do as well have sort of test bench modes where it starts the chip up with no initialization, and that's a good way to see how the boot process will work once you have the actual silicon back. So none of the memories are initialized, but then there's also this what we call the sort of fast mode, which it just preloads everything, rather than having to wait around for ages for it to sort of upload the program and things like that. Just a quick note on the sort of behavioral test design. So like I say, so the firmware runs directly on the M0 in the test bench, and then the expansion region is memory mapped. One thing I kind of just suggest, and I think this is maybe it's a matter of opinion, doing things like this in software where you have sort of structured access to data structures looks a bit cleaner and is a bit easier to debug. And a quick note on the sort of accelerator development, if you're doing this, is adding registers to the memory map is basically free area-wise. You might as well add as much as you can for software visibility. I think it's quite easy to forget when you're developing something in Verilog. You can look in the waveforms, you can access every pin or wire, but when you get the silicon back, you can only see what you can get off the bus effectively. So sort of then how, I guess, with the verification of the accelerator or the expansion region, you can either do it within nanoSoC, and then this is really, I guess, more sort of functional verification or bridge verification, or in terms of you verify externally, whatever method you choose, whether that's sort of formal verification or just functional verification, things like that. And then it's more about testing the integration of nanoSoC. And at that point, it's really just testing the bus interface, the interrupts, and the sort of DMA request, and particularly as well whether the sort of reset or power on state of your accelerator sort of works in the framework. So one of the things, and I think this is one of the kind of inspirations for nanoSoC for SoC Labs coming about, was sometimes maybe you would get into a project and you get all the way to FPGA, and then it's very difficult to transition from FPGA to ASIC. And a lot of the time that comes from relying a lot on the hard IP in the FPGA. What we've done is basically take everything and put it all into the PL side, or the soft IP. That's where nanoSoC goes, including just below the pad ring nanoSoC, and then created this socket around it, which does all the the clock, the resetting, the comms, over to the sort of PS side, or the pink side, particularly with the silence boards. So then really all you're doing in the hard IP is you've effectively got a debugger. That's it really. Why we've done this is then that allows you to take whatever you've put in the FPGA almost directly to ASIC. There's no sort of transition then, really. And where we use FPGA, so for us the FPGA is not the end goal. It's as a sort of verification step really. So one of the ways that we utilize this is with the continuous integration and deployment. So in our Git, this will every time you make a change, or every week or so, you'll build the FPGA image, go to the sort of virtual lab, which is where the FPGAs are all hooked up, download the image, run verification, and then check that it's still working in that. And we have some details about how to set that up as well on the website. Now I'm going to start talking about the ASIC side. So in terms of technology nodes, what we've done so far is the TSMC 65 and 28 nanometer, and the flows available for that. We're currently looking at we're currently starting GlobalFoundries 55 nanometer, and planning to offer sort of multiple backend options. The 65 nanometer work we did pushed for performance mostly over sort of low power or low area really. So the plan is to offer some sort of more balanced options or more low power options. And in terms of how this process works and what technology nodes are available, CMC are going to talk a bit more about that later. The flows that we have available, so we have some reference flows for Cadence. So this is the sort of genus Innovus flow, the Synopsys Fusion compiler, and plans to add for the sort of the design compiler and the ICC2. All of this is on our Git. So this is on the ASIC flow Git repository. These are the sort of generic scripts, which then use some more the sort of technology specific scripts in the projects themselves. So in terms of the backend flow, I know this is, some people probably have seen this 100 times, but just to go over this. So you've got your synthesis, which is importing your libraries, reading all of the Verilog or on the RTL. DFT insertion if used. We've done that in our last SoC. So when we taped on nanoSoC, we had scan chains throughout the whole design. And then mapping these to gates and running some sort of initial optimizations. Placement, so includes setting up the power domains, physically where they're going, which is part of the floor planning as well. And then you're running placement and optimization of those gates. The clock tree stage, this is where you really get into the timing problems. So synthesizing the clock tree and running the clock optimization for the sort of data paths and clock paths. Routing, there's usually some pre-route setup to do before doing that. And then running it, optimizing it, and doing any sort of engineering changes after. And lastly, sign off. Say, this is your design rule checking, your layout versus schematic, static timing analysis, and the ERC. I can't right now remember what that stands for. This I've sort of shown this as a linear path. There's a bunch of backwards and forwards. Usually what happens, and it is not just one step back, it's sometimes 2 or 3, 4 steps back. When we've been working with AIU project, a lot of the time it's going to the clock tree and then it's going back all the way to the RTL. And that's quite common, I think, for that to happen. Something to talk about for those who aren't really familiar with the sort of backend processes. So in terms of synthesis, when you get to this, when you get to the physical level, transistors don't always behave, straightforward. You end up with sort of the corner analysis here, so where you've got some transistors will go slower than others or faster than others. Normally this is down to tolerances in the manufacturing process. It's also down to the supply voltage, the temperature that this is running at. when we do the sort of initial synthesis, we just do this single corner, but when we do the full sort of P&R, we'll do this over multi-corners so that it's really trying to optimize the whole design across sort of full space. Second step is then reading the RTL. So we've got scripts that help make this a lot easier. So it creates a file based on sort of generated scripts, which you can find in here. This design here is then for nanoSoC, it's quite simple. So the power intent is just 2 power domains, which are all the separate supply pins. So there's no worry of power switches or anything like that. It's single clock, well, 2 clocks really. So it's the system clock and then the serial wire debug. And on the 65 nanometer, this goes up to 240 megahertz, which I reiterate here. So in the 28 nanometer when we did it, we've optimized that more for power, so we've kept the clocks the same. And in terms of the synthesis results, we meet timing as expected. The area overall is 0.8 millimeters squared. In this example, so I've used the AES encryption engine example, so it's quite a small accelerator as a sort of overall proportion of the whole. 28 nanometer, couldn't find the synthesis results, but this is a bit of a smaller design. The 65 nanometer ends up as 1.5 millimeters squared overall for the post P&L. And power for this, the kind of note on this, I guess, is this is just the first initial power estimation from switching the whole design a certain percentage. When you run through these tools, if you don't give it any sort of information on net switching, it will just assume that every net switches a certain proportion. I think it's usually 20%, which is quite overestimation of what the actual thing is. I think when we got this back from post silicon, it's more like 3 or 4 milliwatts overall when you're really running it. In terms of, I'm going to go over this a bit quickly. So in terms of placement, the main sort of part of this really is the macro placement and sort of power domain placement. And this ends up being quite an iterative process if you're doing it for the first time, in terms of trying a floor plan out, seeing if the timing works, seeing if it all works, and then going back if it doesn't. So here we've got this sort of accelerator power domain, and these yellow blocks are all the big yellow blocks are the SRAMs, the small ones the ROM. The power planning for it. So the sort of purpose of this, if you've not seen one of these before, when you're supplying a voltage at one of the pins, obviously as you get to the middle, it's going to drop a little bit. And really with the power planning, what you're trying to achieve is that drop is small as possible, or at least within whatever tolerance you set. So usually you'll see these kind of grids of supply rails. And in here, for this, so we've got a ring around the outside on the top metals. So the top metals are usually thickest, so they give sort of the lowest voltage drop. Some of these straps over the top, so they're sort of determined what layer you use by what layer, then you have to connect to the memories sometimes. I mean, you can always do lower ones and upper ones as well, but we found this was fine for this design. One thing that's not always mentioned as well is end caps. You need these at the end of each of your rows. This basically just ties off the well to the rails. And that you end up having sort of separate ones for each of the power domains. And this is what the end of sort of placement looks like. So in terms of the density of cells, you do see a bit of space, but then this ends up getting filled up a lot by the whole cell fixing block buffers. I think this is after initial kind of clock tree optimization. There's not much really to say here, except for using the tools to really debug timing. One of the ways to do this is to look at the clock trees. In this design, it's very simple. Like I say, it's 2 clocks. But you can use these really and look at where physically those clock endpoints are in your design. If you've got any problems, you can maybe change the floor plan to fix that. And routing, I think the main thing to note here is that if you get to the point of routing and you find, congestion's too high, there's always, you can go back and change your metal stack potentially, depending on what's sort of offered. And it's not always something that's, in sort of all of the guides, I guess. The sign off and sort of GDS, again, I'm not going to talk too much about this, but effectively you've got your DSA. In Innovis, this can be integrated with their sort of PBS tool or mental graphics caliber tool. When we did this last time, we had to fix a few by hand. I don't think that's too unusual, particularly in, it was sort of spacing violations in the NWell, PWell that we just had to go in and edit the GDS for. And, at this point, obviously, so CMC will talk more about their services, but then you have a bit of a back and forth in terms of you're sending the GDS over, making sure it's DSA clean, things like that. The test board, like I say, so this is very much mimicking the test bench. The board we created, just to for reference, it's about $3,500 Canadian dollars for 8 boards. Well, 6 of them being assembled with components. And that's all available. The Gerber files for that are all available if you wanted to make that yourself. We're currently updating it. So the old board was fixed really for kind of a 65 nanometer node or a similar node. And what that meant is that the voltages for it, so it's 1.2 volt core voltage and 3.3 on the I/O. What we want to do is make a version where you've got this kind of a main board and a daughter board, where the daughter board you can put in your nanoSoC, and then it's either it's programmable voltages or it's specific to whichever technology you are using. And I'm just going to quickly skip over that, so in the interest of time. So just to reiterate, so nanoSoC reference design, the idea behind it is for entry level ASIC implementation of a SoC. So low cost, so it's roughly about 1.5 millimeters squared. These are the sort of prices CMC have for the 65 nanometer and the 55 GlobalFoundries. Been proven in silicon with custom accelerators, and then there's support as well for analog or mixed signal subsystems. And this, what we've done with it is for the off-chip comms and sort of debug support. This is really just a call to get involved. You can collaborate on any of the projects at any time. You can make your own projects. We have annually SoC design contests to go to tape out. We have these 2 tracks. So we've got the education track and the hardware track. The education track is mostly about your learning journey and how you get on with building an ASIC and how well you share your knowledge and experience. And then the hardware track is more about novel applications or novel designs. So we do have a contest for Canada and the Americas. So this is, again, same track. So you've got the education track and hardware track. If you go to our website under the news category, you'll see this, this sort of heading. If you'd like to join, there's details there on how you join. We're here to help. We're happy to support people who sort of join in the contests, providing technical support, any sort of advice that you need to be successful effectively. We're really here to collaborate. And with that, I'm going to pass over to Oleg.
Hey, can you guys hear me? Yeah, great. Daniel, since you're controlling the slides, maybe I'll just tell you when to go to the next slide and then something like that.
That's fine. Yeah, that's fine.
Yeah. So I'll go very quickly about most of the slides. Like my talk is going to be mostly high level about CMC and how you can get started with SoC design, because that's where CMC supports like the training and getting started aspect of it. So who we are and what we do, for the most purposes, like for this project collaboration, so CMC would be playing like a supporting role, more complementing SoC's SoC Labs capabilities. So CMC Microsystems is a Canadian nonprofit organization supporting researchers in microelectronics and other advanced technologies. Since inception, we've expanded into several other technologies or competencies that you can see, like signal and photonics, MEMS, IoT, assembly and packaging, and even quantum hardware. But again, for the purposes of this meeting, I'll be mostly focusing on the microelectronics aspect of it. And very briefly, we provide a wide range of design and prototyping services and access to fabrication for researchers or small companies that normally can't really get them themselves because it's an issue sometimes for when you go to TSMC or GlobalFoundries and you ask for fabrication and you can't really get it easily. So this is where we come in. If you're familiar with your practice, we sort of provide a similar service, but with additional set of peripheral services that John and Daniel mentioned. And we take care of the NDAs, with the foundries, the PDKs access, the IP access, for example, how to set up the ARM IP, standard design environments, which I'll talk about in a second, all that good stuff. And although you can see that most of our users are the Canadian researchers and companies, we also work with many non-Canadian organizations. We can provide services globally. It just won't be subsidized by the Canadian government. And most of the value we usually generate are for researchers and small companies or new designers that need to navigate how to get their first chips fabricated. So like we are sort of like a teaching and getting started role, at least that's how we see ourselves. Next slide. Great. So our biggest value and our backbone is this network of suppliers. We're a broker to fabrication and other services. And so our intimate knowledge of their capabilities is a critical part of how we help our clients. So we have over 100 suppliers in several countries across the globe. I won't really go into details for every single technology we support. There's a lot of them, but only what's really relevant to this talk. But if you are really interested, feel free to contact us afterwards or on our website. Next slide. So why CMC? So to quickly reiterate, we can help you with access to technologies like PDKs, IP, ARM IP, or other like IO libraries, or other relevant resources from commercial foundries. We help newer or smaller design teams set up their design workflows that are common to industry. So getting them industry ready, for example, getting them up and running really fast within a couple of days. And we've been doing this since the 90s. So I think we have a little bit of experience in that. We also don't just help with the administrative parts. We have about 5 technical design teams, about 40 people in those teams, who works and support either design work, cleanup, or backend, and can help with navigating like new designers how to get started. And we also offer consulting and engineering services, especially with what we have experience with, and generally provide our services throughout most of that early design or product development cycle. Next slide. Okay, so I'll quickly go over into a little bit more detail about some of the services that Daniel and John mentioned. But if you are, again, interested in deeper dive, please contact me. Our cloud EDA environment service, it's exactly what it sounds like. This is where we take a small research team, your team, or design team, that company within the company, and get them ready for a chip design in a couple of days. So you simply need to have your own design team, and then agreement with design tool vendors like Cadence, for example. We need to have those tools, and we do the rest. So and if you don't have the tools, we can also help getting you started with that. But what we do is we will consult with you what technology you need. Or if you already know that, we'll take the tools that you have, the PDKs for those foundries, the IP, so ARM or IO libraries, and we put it all on the cloud design or on the cloud environment with the correct versions, using our pre-configured scripts, so you can just start making your chip. If you don't have the NDAs or other legal paperwork for these foundries, that's something that we can help and get everything going for you. And we use typically we use public cloud, like AWS, for example, or something else, and we set up the environments on those on the public cloud frame. Okay, so next slide. Great. And then jumping into the prototyping fabrication, this is another core service that we provide because we are a broker for fabrication in that aspect. We support many technologies from 12 foundries worldwide. I think I've only listed a few here because they're more relevant for the SoC and what was talked about, but there's quite a bit that we support, including the GF nodes, smaller nodes up to 12 nanometer, for example, TSMC nodes. We support we see about 300 to 400 designs a year. And we're seeing an increased demand actually for lower nodes, and also open source technology such as the 180 MCU. Although this support for open source is still not really popular within industry, but many researchers are starting to take advantage of it. So if you do need help with that, we can help. And then obviously multi-project wafer is something that we offer. It's very popular within researchers. But some of them are actually starting to use full wafers, which we also have helped, because it's kind of useful for wafer scale packaging or other chip stacking or very unique types of integrations or devices. So if you need prototyping SoC devices, we can definitely help. Next slide. So I'm gonna go through this kind of quickly for the sake of time. But our ASIC design services are pretty broad, including, we can do primitive design, IP block integration or layout verification, all that good stuff. But most of the microelectronic designs usually we work with are on back end. We're a great partner if you have, if you have already created an architecture, and we can fill in this gap or the skill gaps within your team. But yeah, our goal is to primarily help you get started on that first prototype and give you directions how to move forward. Next slide. And another strong focus that I want to bring up is the packaging integration. We've begun offer complex or custom packaging services. We can obviously help with standard plastic packages, wire bonding, flip chip, but we've worked on a variety of projects for SoC devices, such as chip stacking, heterogeneous integration devices, interposers, or a larger wafer level integration. We have one project where we're doing a multi-project prefabricated silicon breadboards, for lack of a better word. We have prefab wafers for full TSV wafer arrays, and we can easily put down metal RDL on it, kind of like a lowish cost rapid prototype interposer if you want to do some 2.5D integration. And we offer that as an MPW service. Anyway, we have a ton of packaging options if you are interested in making your device. Next slide. Yeah, so this is the last thing I want to talk about, which is the training, which is a big part of CMC and our core values. Our intent is to teach you how to get everything up and running with your chip design. So we have many courses and workshops and base camps, as we call them, available to help train you on latest industry and standard PDKs. A base camp is essentially like a course which includes fabrication of a prototype at one of the foundries, such as GF 12 nanometer, as listed here, for example, for FinFET training. That way you actually go through that full tape-out experience, all the nuances associated with that, and we provide and then at the end of the course, you provide us with a test of your chip. Yeah, and then probably would be good to partner with SoCLabs to provide more courses for this audience in the future. So something that we can probably explore together. And next slide. Great, so this is CMC's contact information. So I went through this pretty quickly because we're short on time. But if you do want to contact us, there's our information. And please also speak with SoC Labs because we're going to be partnering together on these projects. And that's it.